Now we finally get to approach what I would consider to be the heart of statics. I'm talking about equilibrium of rigid bodies. And to determine forces on rigid bodies, we will use free body diagrams. So after today, you should be able to identify support reactions and you should be able to draw a free body diagram. As usual, there are many other resources in the slide deck. Please look at them, go through the example problems in the group solving problems, as well as watching the rest of my videos of examples related to this section. What are the applications of what we're going to study? Well, imagine ramps like these at the back of some type of a truck or trailer, and how would you know what size pins are needed in order for the ramps to pivot? How do you know how big around they would need to be? How do you know how thick the cables need to be that support the ramps? How would you calculate a required size? Well, you won't really be able to calculate a required size until you get to strength of materials. However, in this class, you will learn how to calculate the loads. In other words, the effective forces that are within the cables and on the pins and all those sorts of things, given, say, the weight of the ramp and the geometry of the situation. So how do we do that? Well, it's pretty simple. We use free body diagrams. Now, there's several steps along the way to go from a real situation to a solution that is reasonable. Now, there's always idealization, simplifications that we make, that you will probably struggle with because you probably have some intuition about what's going on in these situations. And you might think, oh, well, the pin that allows the ramps to pivot, those pins have some friction. Yeah, that's true. And therefore, those pins cause a little bit of a moment that tends to help hold the ramp up. But it's not significant by comparison to the force applied by the cables to hold the ramp up. And so we neglect things like friction at pins where those pins can rotate. So is the solution we come up with perfect? Of course not. And of course, if your intuition also says, well, wait a second, this truck's going to go bouncing down the road and there's going to be all sorts of forces applied to the ramps. That's true, but that's dynamics. Right now we're in statics. You got to learn to walk before you can run. So that's where we are. So there's really two steps to coming up with free body diagram. And the free body diagram is the key to solving for any unknown forces. And unless you get the free body diagram right, you're not going to get the right forces. You've got to get that correct and identify all the critical forces overall. So a step kind of before the free body diagram is an idealized model of the real situation. So looking at these two diagrams, you might wonder, well, which one's which? Which is the free body diagram? Which is the idealized? Well, it's the one in the center that is the idealized diagram. And there's probably a lot of detail in the real world that's not present on this diagram. For example, if you look at the cables in the photo, you notice there's some sort of shackle or something at the end of the cable, but that has been neglected, and we've just drawn the cable as if it's connected via pin to the bed of this truck or trailer, whatever it happens to be. The reason we do that is because we're not really overall interested in what that shackle does and how it affects the forces. Yeah, it does some, but really what we want is the force in the cable. We're interested in how much tension that cable is applying, and from there we can go into more depth, considering the shackle itself, that little round piece, and the effect that it may have in the connection to the bed of this whatever type of hauler machine it is. But we still will get a reasonable answer for the tension in the cable, and that shackle is not really going to change the tension in the cable, because if you consider the free body diagram all the way at the right, what you'll notice is that the tension force is applied where the cable connects to the ramp. Now, another skill that's required is selecting the correct free body. And some of these things, you just have to try it, and you end up selecting the wrong free body. You find, oh, well, this is not going to lead to a solution, so I'll choose another free body. So there might be a little bit of trial and error. I hope that the examples I work through will help you see how to choose a good free body so that you can solve whatever problems presented in an efficient manner. But this is something you'll have to work at, and you will have to, well, if you're like me, you'll have to fight your intuition along the way to, how can I explain this, to come up with a reasonable free body diagram that can be solved. And you might feel like, well, this is not right because we're neglecting some things. That's true. That's true. You're not going to get a perfect solution. However, let's say that you are considering two jobs. People usually understand money, so let's use this one. You're considering two jobs. One pays you $20 an hour, the other one pays you $20.05 an hour. Are you going to go for the $20.05 an hour job when it's a job you hate, or are you going to go for $20 an hour for a job that you think you're going to like? Obviously, the one you like, right? And that's only 5 cents out of $20. In other words, sometimes things are small enough that you can neglect and they don't make a big difference. And that's what we're trying to get at here. We're trying to come up with an idealized model of what's going on that we can apply a free body diagram to and get reasonable results. So maybe we calculate, let's just make up some numbers. They say that these ramps have a weight of 400 pounds each. Okay, fine. Let's just say for the sake of argument that we calculate that the tension in the cables is, I don't know, 600 pounds. We'll just make it up. Now, if the actual number is 601 pounds, so what? If it's 599, what difference does that make, right? By neglecting the friction in the pin, we're going to end up with a slightly higher force in the cable. But that's okay. We're trying to get in the ballpark and get close enough, because if you specify a cable for this application, you're not going to select one off the shelf that's rated for 600 pounds, right? You're going to add a factor of safety on top of that. So anyway, there's a lot of practice for you to do in order to become good at what's the idealized model. Therefore, then, what's the free body diagram? And then let me solve that and come up with a reasonable answer. So this is really an important part of the course, and I hope that you'll spend some time thinking about your choices as you work through the homework, and spend some time thinking about why I chose the things I chose in the example problems that I work as well. Hopefully you'll catch on to it, and if you have questions, feel free to ask, of course. So here's another application where we've got two smooth pipes. These things can roll. They're smooth, meaning that we will neglect friction. Each one has a certain mass, and they're supported by the tines of a forklift. So how do we determine all the reactive forces? What do I mean? Well, these things are sitting on top of the tines, so they must be applying load to the tines. Therefore, the tines are reacting and providing load to support these smooth pipes. So how do we do that? How do we calculate the magnitude of those forces? Well, we'd have to make a free body diagram. And here's an interesting thing. You don't, even though the two pipes are separate, you don't necessarily have to separate them out as two separate free bodies. You can take them together as a single free body. I realize they're not technically connected to one another, but they do apply force to each other, and those forces are internal to the two. Because think about it, whatever force the upper pipe applies to the lower, whatever force B applies to A will apply an equal and opposite force to B. This is one of Newton's laws. And so if we don't worry about it because that's an internal force, we can calculate the external forces applied to these pipes and determine, how strong the tines of the forklift need to be, or how much force in a cylinder is required in order to actually raise this load. So how do we make an idealized and free body diagram, well, an idealized model and a free body diagram of this situation? Well, the first thing to do is just draw a simplified version of it, and that's what you see in the middle. And then after that, consider the forces. Like I said, there's a little bit of practice required to come up with appropriate forces. Notice something interesting. There's a force F on pipe A. There's a force P on pipe B. And since their weights are equal, you might be tempted to say, well, F and P are equal. Don't make assumptions like that. That's not necessarily a valid assumption. It may be correct in this case, but it's not correct to just assume that from the very beginning. Another thing to note is that there's no friction shown here. Why? Well, it's kind of like a code word, I guess, if you will. When a problem statement tells you that something is smooth, what they mean is neglect friction. That's what they mean. So there's some learning you'll have to do to begin to recognize the various ways that information is conveyed to you by a problem statement. And again, hopefully my example problems will help you understand those various conventions, so to speak. When we talked about particles, we were talking about forces on those particles, and those forces had to all pass through the same point because the particle had no size. But when we talk about bodies, not only do the forces not necessarily have to pass through the same point, but also there can be moments applied. You can't really talk about the rotation of a particle. That doesn't make any sense. But rotation or tendency to rotate of a body, a rigid body, is certainly a valid conceptual tool that we need to employ. Now, just like forces on a particle, for the sake of statics, for that particle to not accelerate, the sum of the forces has to be equal to zero. So we still have those equations of equilibrium that we had before, that the sum of forces in all three directions, if we're talking about a three-dimensional problem, the sum of forces in all directions must come out to zero. But now we've got another set of equations where we can talk about the sum of moments in all three coordinate directions, at least in three space. So actually now we will have 6 equations of equilibrium to deal with. So the first thing to do is create an idealized model, and that's been done for the ramp here. Second, draw the free body diagram showing all of the external forces, so all the active forces and all the reactive forces. For example, the weight G, or the weight at G, is an active force, or it's an external force that's applied to it. You know, if you grab onto the end of the ramp and you hang on it and do some pull-ups on it or something, that is also an active force. And it's not because you're doing pull-ups. If you just hang on it, that's an applied force, a force that doesn't necessarily have to be on the ramp. But the tension in the cable will increase to compensate for your body's weight, and therefore the tension is a reactive force. It reacts to other forces applied to the body. Similarly, AX and AY are also reactive forces applied to the body. And it's really important to distinguish between those two because there are very different things. Then finally, once we've got our free body diagram, we simply apply the equations of equilibrium to solve for any unknowns. Now, this is a problem that lends itself to two-dimensional analysis. In two-dimensional analysis, you'll have a sum of force equation in the horizontal direction, the x direction, and a sum of force equation in the vertical direction, the y direction. So you'll have 2 sum of force equations. You'll only have 1 sum of moments equation because all moments must be perpendicular to the plane, to the xy plane in this case. Those are the only moments that can be generated by these forces because all of these forces lie in the xy plane and so can only cause a moment out of the plane. So here's an idealized model of a beam, and it's simplified because we don't have all of the information about the beam. For example, how tall is the beam? Who knows? It doesn't really matter. We know how long the beam is. We don't know exactly what the details of the cross-section of the beam are. It looks like an I-beam from the side, but which I-beam? There are wide flange beams. There are, just your regular S-shapes. So we don't really know the details about it. So this is already a simplified model of reality. We'll notice that there's a load of 1,200 newtons applied out at 2 meters, and the overall beam length is 6 meters long. To draw a free body diagram, what we'll do is draw an outlined shape. So this is really important. We've got to imagine that the body is free. It's just hanging there in space. And the reason we imagine it that way is we're trying to determine what support reactions are required to keep this beam in equilibrium. Because think about it, the heavier the beam is, the more force the wall is going to have to push up with on, at A in order to support the beam. Or the heavier the load, the 1,200 Newton load. What if it's a 2,400 Newton load? Well, then that's going to require more force at the wall to support the beam. But not only that, there's also the weight of the beam that is applied, and there's going to tend to be a moment because both the 1,200 Newton load and the center of gravity of the beam are out a distance from point A, and the only thing that supports this beam and prevents it from falling is the wall. And so the only place that forces and moments can be applied to this beam to hold it in equilibrium is at the wall. And therefore there's an AY, potentially an AX, a horizontal force. Of course, in this case, if you have some intuition, you might look in and say, yeah, actually the horizontal force AX would be 0. The wall doesn't have to pull or push on the beam along the length of the beam. And then the moment at A is the other reaction that the wall must apply in order to prevent the beam from rotating downward. So the key to free body diagrams, or one of the keys I should say, is that you've got to realize that you're trying to draw forces and moments that act on the body. You don't want to draw any forces that the body applies to something else, only forces applied to the body, because there will always be equal and opposite forces. For example, even the weight, there is an equal and opposite force. Well, what does it act on? Simple, Earth. So if the Earth is pulling down on this beam with 981 newtons, the beam is pulling up on Earth at a magnitude of 981 newtons. And whatever it is that's applying the 1200 Newton load, this beam is applying an equal and opposite 1200 Newton load to that other object. And that's a really important fact to realize, that there are always equal and opposite loads, but the loads we're interested in, whether they're reactive or ones that are applied, the loads we are interested in are loads acting on the body, not from the body onto other things. So then we show all the external forces in couple moments. And as I said, that can include applied loads, support reactions. Of course, the weight of the body is also commonly included. Now, frequently, the weight of the body is negligible by comparison to other forces within the body, and so we simply will not include it in our equations. If you're given the mass of the object that you've taken to be a free body, and you know the direction of gravity, that gravity acts, you should include the weight for the sake of completeness. But sometimes that information is simply not given because it would be very small by comparison to the external forces or reactions that are applied to the body itself. So continuing with our free body diagram, what's the next step? Well, label all the loads on the free body diagram. You need to have something you can call everything. And sometimes you'll have a force or a moment and you won't actually know its direction, you just know where it's applied. In that case, although your book doesn't show this, what I recommend is an arrow that is curved. So not just a round arrow, but something that looks sort of like an S, indicating you don't really know the direction of the force or the moment. Now, those won't be very common in the course, but they might be useful. That concept might be useful for your project. Most of the time, we know the directions of the forces in the problems we solve in this class. So you should definitely do your best. If there's some reason that you know the direction of the force, certainly include that information, because force is a vector, and the direction of that force is just as important as the magnitude of the force. And then for anything where you don't know forces, still often you will know directions of those unknown forces, and all you really don't know about the force is its magnitude. And in that case, just call it something reasonable. For example, at point A, AX and AY were used to indicate the force at A on the body in the horizontal and vertical directions. And then MA is the moment at A. Since we're working with a two-dimensional problem here, the moment at A is the only moment to consider because it's the moment that would come out of the plane. We wouldn't have any in-plane moment components to consider. Now, dealing with support reactions in two dimensions can be a little bit difficult. There is a table in your book, and I always allow my students to use their books in exams. So it's open book. Now, don't think that's going to make the exam easy. That's just for your convenience. I'm horrible at memorizing things, and I don't really see a point in memorizing things, especially when you're trying to learn how all these things work. So you're welcome to use your book. However, occasionally there are pages that I will tell you should absolutely put a tab in that page so that during an exam, which is timed, you can find the page very quickly. So I don't remember the page number, but table 5-1 in your book is absolutely a page that deserves a tab for sure. So go there now, please, locate the page, and the value in that page is that it shows you, given different types of joints, connections, if you will, between various bodies, what kind of forces or moments can be transmitted between the two. For example, if you have a pen, there's no way that that pen is going to have a significant moment, and so we simply don't draw a moment. Just like with the ramps a moment ago, or I should say a second ago, just like with the ramps, we neglected the friction that the pen would cause, and therefore any moment or torque that would be applied to the ramp from the pin. And so you see the center smooth pin or hinge example, so you see the simplified diagram, and then you see the forces that can be applied at that pin Fx and Fy. But if you have an attachment that is fixed to a support, then not only can there be a force in the horizontal vertical direction, there can also be a moment out of plane that tends to provide support for the body. And you see an example there with a simple support where there is rolling contact between the inclined plane and an extension of the body. And the interesting thing about this is that force can only be applied in one direction, because think about it. These wheels are going to roll up and down the incline. They can't include any force up and down the incline. Therefore, that entire assembly that has wheels cannot apply force parallel to the ramp. Rather, all force from the ramp has to be normal to the ramp itself. And that's why it's drawn that way. But there's more examples than this. Do look at Table 5-1. Please do tab the page. And as you go through your homework and you're looking at example problems, have the book open to this page so that you can understand how to select the various reactions that are possible given the type of support that a body actually has. You'll get the hang of it fairly quickly, I think, and you probably won't have to refer back to the table for the entire course. But for now, it's a good page to mark. There's another page, and again, I don't remember the table number on this one or the page number. There's another page for three-dimensional support reactions, and as I recall, it's in the same chapter, maybe at most 10 pages away. If you wanted to, you could go ahead and tab that page as well. So generally, when a support prevents motion, prevents translation motion, which just means linear motion, then force is developed on the body in order to prevent the body from moving. However, if rotation is what's prevented, then that's done by a couple moment or a moment to support the body.